The Standard Model is often described as the rulebook of the subatomic world. That sounds simple, but what makes it extraordinary is not just that it names particles. It gives a mathematically precise framework that predicts how those particles behave, interact, and transform under three fundamental forces: electromagnetism, the weak interaction, and the strong interaction. If you've ever wondered why atoms hold together, why radioactive decay happens, or what creates the energy in stars, you are already standing on Standard Model territory. The model did not appear overnight. It emerged over decades as theory and experiment corrected each other. Physicists proposed symmetries, tested them, discarded what failed, and refined what worked. By the mid-1970s, the core structure was in place, and later discoveries strengthened confidence in it. But here is the key tension we'll explore. This framework is incredibly successful and still incomplete. It explains enormous amounts of data with astonishing accuracy, yet leaves major cosmic mysteries unanswered. So the Standard Model is not the final chapter of physics. It is the most successful middle chapter ever written. To understand the model, start with its building blocks: matter particles and force particles. Matter particles come in two families: quarks and leptons. Quarks combine to form protons and neutrons, which then form atomic nuclei. Leptons include the electron, which orbits nuclei, and neutrinos, which are ghost-like particles that pass through matter with barely any interaction. These particles are organized in generations, like repeating patterns with increasing mass. The first generation makes ordinary matter around us. The heavier generations are unstable and usually appear only in high-energy environments, like cosmic rays or particle accelerators. Force particles, called gauge bosons, mediate interactions. Photons carry electromagnetism, gluons carry the strong force, and W and Z bosons carry the weak force. This classification is not just a taxonomy chart. It encodes deep symmetries in nature. Those symmetries tell physicists what interactions are allowed and with what strength. In that sense, the particle list is more like a periodic table fused with a grammar of reality. You don't just learn who exists, you learn who can talk to whom and in what language. The strong force is the glue of the visible universe. It is described by a theory called quantum chromodynamics, or QCD, inside the Standard Model. Quarks carry a property called color charge, and gluons transmit the strong interaction between them. Despite the name, color here has nothing to do with visual color. It is a technical label for how quarks interact. QCD has a bizarre but beautiful feature: quarks are effectively confined. You can bind them into groups like protons and neutrons, but you never isolate a single free quark in everyday conditions. Pull quarks apart hard enough and, instead of freeing one, you create new quark pairs. The force also behaves oppositely from electromagnetism at very short distances, a phenomenon called asymptotic freedom, where quarks act more independent as energies rise. This behavior was one of the major theoretical triumphs that helped shape the Standard Model. It explains why nuclei can be stable while still allowing high-energy collisions to probe internal structure. So when people say matter is mostly empty space, remember that the strong force is what gives nuclei their resilience and ultimately gives ordinary matter much of its mass-energy character. Electromagnetism is the most familiar force in the Standard Model because we experience it constantly. Light, chemistry, electricity, magnets, and even the structure of atoms all depend on it. In the model, electromagnetism is carried by photons, massless particles that allow electromagnetic influence to travel long distances. But the real conceptual leap is that electromagnetism and the weak force are not fundamentally separate at high energies. They are unified in what physicists call the electroweak framework. At lower energies, the symmetry appears broken, and the forces look different to us. Electromagnetism remains long-range with a massless carrier, while the weak force becomes short-range because its carriers, the W and Z bosons, are massive. This isn't merely a clever mathematical trick. It gave concrete predictions about neutral currents and the properties of W and Z particles that were later confirmed experimentally. That predictive success matters because in physics, elegance alone is never enough. A theory earns trust by surviving measurement. The electroweak unification is one of the clearest examples where abstract symmetry principles produced real, testable outcomes that nature then confirmed. The weak interaction is subtle but indispensable. It governs processes where particles change identity, like a neutron turning into a proton in beta decay. Without weak processes, stars would not burn the way they do, and the cosmic history of elements would look radically different. The weak force is mediated by W and Z bosons, which are heavy compared with photons, making weak interactions short-ranged and less obvious in everyday life. Yet at fundamental scales, this force is central to how matter evolves. The Standard Model predicted detailed properties of weak neutral currents and the behavior of these bosons before experiments measured them directly, and those predictions matched with striking precision. This was a huge credibility boost. It demonstrated that the theory was not just patched together from known results, it could see ahead. In practical terms, weak interactions also reveal why neutrinos are so hard to detect and why certain decays are rare. Their probabilities, called cross-sections and branching ratios, can be calculated and tested. That feedback loop between equation and detector is where the Standard Model proved its strength again and again: small signals, hard measurements, and surprisingly accurate forecasts. Now we arrive at the Higgs field, often misunderstood as just another particle story. The Higgs boson is important, but the deeper concept is the field itself, which permeates space. In the Standard Model, this field is tied to spontaneous symmetry breaking, the mechanism that lets W and Z bosons acquire mass while preserving the underlying gauge structure of the theory. Without that mechanism, electroweak equations would fail to describe reality as we observe it. Fermions, like quarks and leptons, also gain mass through interactions with the Higgs field via coupling strengths. The 2012 discovery of the Higgs boson at CERN was therefore not a random add-on, it was a critical missing confirmation of the model's architecture. It validated a mechanism that had been mathematically embedded for decades. But discovery did not close the book. It opened precision questions: are Higgs couplings exactly as predicted? Is the Higgs alone, or part of a larger sector? The Standard Model currently says one thing: many beyond standard ideas suggest additional structure. So the Higgs is both a triumphant confirmation and a doorway to possible new physics. One reason physicists admire the Standard Model is its predictive discipline. It has repeatedly anticipated particles and interaction patterns before full experimental confirmation. The top quark, observed in 1995, and the tau neutrino, confirmed in 2000, fit expected slots in the framework. Their discoveries were not lucky guesses, they were consequences of consistency requirements and prior evidence. This track record created a high bar for any challenger theory. To replace or extend the Standard Model, you must not only explain new anomalies but also preserve the immense body of successes already achieved. This is harder than it sounds. Many speculative models are imaginative but stumble when matched against precision constraints. The Standard Model has survived because it is internally coherent and empirically overtest. Think of it as a bridge that has carried an unbelievable load without collapsing. You can still argue the bridge does not reach every destination, but you can't deny its engineering quality. In research culture, that distinction matters. Scientists are not searching for novelty for its own sake, they are searching for better explanations that still honor what has already been measured correctly. So where does the Standard Model fail? First, gravity is missing. The model is a quantum field theory framework for three forces, but gravity is best described by general relativity, a geometric classical theory of spacetime curvature. These descriptions are both successful in their domains yet mathematically uneasy together, especially at extreme scales like black hole interiors or the early universe. Second, dark matter. Cosmological and galactic observations imply a large amount of invisible matter shaping structure formation and gravitational behavior. The Standard Model does not include a particle with the right combination of properties to explain this component. Third, the matter-antimatter asymmetry problem. The universe appears dominated by matter, but basic early universe reasoning suggests matter and antimatter should have been produced almost equally. Standard model sources of CP violation exist, but they seem insufficient to explain the observed imbalance. Fourth, dark energy and accelerating cosmic expansion lie completely outside the model's core content. These are not minor loose ends, they are central to modern cosmology. So while the standard model is deep, it is not complete. It is a powerful local map, not the whole atlas. Neutrinos offer another clear sign that the minimal standard model needed extension. Originally, neutrinos were treated as massless. But neutrino oscillation experiments showed that neutrinos can change flavor as they travel, and that phenomenon requires non-zero mass differences. In plain terms, neutrinos are not exactly what the simplest original setup assumed. Physicists can extend the framework to incorporate neutrino masses, for example through additional terms or mechanisms like seesaw constructions, but those additions point beyond the most minimal standard model form. This is important philosophically. A theory can be exceptionally good and still require revision when data demand it. That is not failure, it is science functioning properly. Neutrino physics also hints that tiny effects can reveal profound structure. Because neutrinos interact so weakly, they are hard to study, yet they may hold clues about early universe processes, symmetry-breaking history, and perhaps even links to matter-antimatter asymmetry through leptogenesis scenarios. The lesson is that frontier physics is not always at the highest energy only. Sometimes it is in the faintest signals that refuse to fit old assumptions. If the standard model is incomplete, why has finding new physics been so difficult? Because the model is not fragile. It is robust across an enormous range of experiments, from collider measurements to precision decay studies. Any new theory must thread a narrow path, different enough to solve unresolved mysteries, but subtle enough not to spoil established predictions. That tension drives modern strategies. Some searches push to higher energies, hoping new particles appear directly. Others focus on precision, looking for tiny deviations in known processes that could signal hidden effects. This includes flavor anomalies, dipole moments, rare decays, and Higgs coupling measurements. Researchers also test ideas like supersymmetry, extra dimensions, composite Higgs models, and dark sector portals, each offering ways to extend the standard model while preserving current successes. Most candidates face intense constraints, but that is progress, not stagnation. Eliminating wrong paths sharpens the right questions. The current era can feel paradoxical. The better we measure, the harder it is for novelty to hide, yet the bigger the unexplained cosmic questions remain. That paradox is exactly what makes this chapter of physics so intellectually alive. A useful way to conclude is to treat the standard model as both masterpiece and invitation. It is a masterpiece because it unifies diverse phenomena in a coherent quantum framework and delivers predictions that repeatedly match reality at high precision. It is an invitation because its very boundaries define the next scientific missions: quantum gravity, dark matter identity, the origin of mass scales, the matter-antimatter imbalance, and the true role of neutrinos in cosmic history. In education, the standard model teaches how deep symmetry principles, mathematical consistency, and relentless experimental testing can build reliable knowledge. In research, it teaches humility. Nature can be elegant, but not always in the way we first expect. For viewers, maybe the key takeaway is this: fundamental physics is not a story of one final formula discovered once and for all. It is a living process where each successful theory becomes a platform for better questions. The standard model gave us unprecedented clarity about the microscopic world. Its unanswered questions are not cracks to dismiss it. They are signposts pointing to whatever comes next. If you found this helpful, please like this video and subscribe for more explainers.